One of the most common instruments associated with nanotechnology is the Scanning Tunneling Microscope. And this instrument was invented in 1981 in IBM in Zurich. And what this instrument allowed us to do was map out where atoms were in nanostructures, materials, and semiconductors. So STM has a number of different uses. It's also used for atomic manipulation and also looking at electronic states in structures. However, I'm going to put those into a different video. And in this video, I'm just going to give a brief introduction to how STM is used to image a surface and look where atoms are in that surface. So the STM consists of a sharp metal tip made either of platinum iridium if the technique is being carried out in air, or if used in a vacuum system where there's no oxygen, you can use a tungsten tip which can be etched to a much sharper point. However, if introduced to oxygen, it tends to oxidize, which removes the property of the tungsten, which allows it to be ideal for using in an STM. So the way an STM works is that the tip, or the tungsten probe, or just refer to tungsten for this video, is mounted onto a material which is called a piezoelectric material. And these materials alter when an electric voltage is applied across them. So when a voltage is put across a piezo material, it grows in certain directions, which means we can use a piezoelectric material with a tip attached to it to be able to move that tip very small amounts. So typically this is about 0.1 of a nanometer. We can move the tip in any direction, so that's up and down and left and right. And the more voltage we can move this tip further distances, so we can move it in 0.1 nanometer increments and scan across a surface. So what an STM does is also applies a voltage to the tip and then lowers the tip towards your surface. So if the tip was to make contact with the surface, you would get a current flowing, a conventional current that is, where the electrons are flowing from the tip into the sample, or if you reverse the bias or the voltage, the electrons will flow out of the sample into the tip. However, there is a phenomenon known in quantum mechanics as quantum tunneling, and this is where an electron, or a particle, can jump from a place where that it's classically allowed across a barrier where the electron is classically forbidden and into another area where the electron is classically allowed, and this process is known as tunneling. So I'll make another video about the quantum mechanics and quantum tunneling and explain those concepts there. But what we mean as far as STM is concerned is when the tip is very close but not in contact, so we're talking less than a nanometer, the electron jumps from the tip into whatever we're looking at, whatever the sample is, and that little air gap of less than a nanometer is the classically forbidden region. So this does produce a current, and it's the tunneling current, but it's very small. It's normally in the region of nanoamps. And what we can do with STM is move the tip down so it's within a nanometer of the surface, measure the current, and then as we move the tip sideways, we can re-measure that current and see how much it changed. So if the features of the surface become closer to the tip, so you're going over the top of an atom, you will get an increase in the tunneling current. So your current maps out where the atoms are in your sample if you're moving your tip in increments which are smaller than an atom, which about 0.1 of a nanometer is. So you can see this animation which shows that. Another mode we have is where you adjust the height of the tip to maintain the tunneling current. So the tip is actually now mapping out the surface, and this is the difference between two modes called constant height mode and constant tunneling mode. So again, if you look at this animation, you can see the tip moving along, adjusting its height so it always maintains the same tunneling current, and this is what maps out where the atoms are in a surface. So this image I'm showing you now is some STM that I did on a silicon wafer, and it shows where the different atoms are. This is a crystal structure called 7x7. So what you're actually looking at is not the actual atoms, you're actually looking at where the electron cloud is in the whatever your sample is. But your electron cloud is going to be surrounding your atoms, so this is how you can image atoms, and this was the first time we were able to see atoms, or find a way of being able to image atoms.